So section 3.1 are fundamental concepts of linear functions. So a linear function can always be written of the form y equals ax plus b. Some of you, if you've taken other math classes in high school, may have seen it also written as mx plus b. So we tend to change the names of these letters around, but what does not change is their position in the formula is actually more important than necessarily the name that they're given. So a is the slope, or the quantity attached to the variable is going to be the slope. So a or m, or we could use another letter if we wanted. And b is the intercept. So the constant is the intercept. So functions where the ARC are constant are linear function and the ARC is the slope. So when we talk about average rate of change, right, if the line is constant, has the same slope everywhere, then we refer to the ARC as the slope. The y-intercept, or the vertical intercept, is where the line crosses the y-axis, and it's going to be located at 0, b. That's what b is telling you in this equation. And the x-intercept is where the line crosses the x-axis. So just to see a visual representation of this, if I have a line, then 0, comma b, right, is your y-intercept, where it's crossing the y-axis, and x, comma 0 is crossing the x-axis. So whenever we talk about intercepts of a function, what we're really saying is, well, where should we put the 0? Does the 0 belong in the x direction, or x position, or does 0 belong in the y position? So for example 1, let's find the intercepts of this function. So the first one, the y one, is usually easier to solve. It's always easier to plug x into something. So f of 0 is going to be 6 times 0 plus 36, which is just going to give us 36. So 0, 36 is the y-intercept. If we want to get the x-intercept, well, that means that we set it the function equal to 0, because y is 0. So 6x plus 36 equals 0. 6x will equal negative 36, and x will equal 6. So negative 6, comma 0 is the x-intercept of this line. So you just want to make sure when you're doing problems that you don't mix up the x and y intercepts. And I find that drawing a little sketch kind of helps me keep it straight. So let's look at another example of how to deal with a line in a word problem, right, or an application setting. So Julie has $1,000 or $1,025 in savings on June 1st, 2010, when she graduated from college. Her new job will pay her $2,200 per month after taxes and monthly expenses. So answer the following. Find a linear function that gives Julie's net income. So she's making $220 per month. So that is actually going to be our slope. $2,200 per month. So that is a rate of change. That would be the average rate of change in this case, as she gains $2,200 a month. She starts, though, with her initial savings. So at time 0, right, her intercept is actually $1,025. So before she even gets her first paycheck, she already has that money. So we can write a linear function, f of x is 2,200x plus 1,025. So in month 0, she's got what she started, and then every subsequent month, right, she'll add $220. How much money will she have made by the end of October? Assume she's paid on the 15th of every month. So this means that if June 1st, right, is when she graduated, her new job, we'll assume, paid her on June 15th. So she'll get a paycheck in June. She'll get a paycheck in July, right, in August, in September, and October. So June, July, August, September, October. Make sure I didn't skip any months there. So that will be at x equals 5. So if we put 5 into our equation, she will have made $12,025. So how long until Julie has $25,000? So we could set this equation equal to 25,000 and solve it algebraically, but we could also use our calculator to do this. So the first thing that I'm going to do is I'm going to go into my y equals, and I'm going to enter the equation into y1. So I'm going to say 2200x, right, plus 1025. And I want to know when she has $25,000. So I'm going to set y2 equal to 25,000. Then I'm going to go to my window and I'm going to adjust my x scale. So we don't want any negative x's here. So I'm just going to start the minimum x at 0. And let's go out 18 months. Let's say a year and a half. See if that works for us. And then I'm going to graph it. Well, I don't see anything. So if I go to Zoom, Fit, which is at 0, right? It's going to adjust the Y scale for me so I can actually see both of these graphs. So there's her earnings, right? And there's 25,000. So now, if I go to second, calculate, intersect, I grab the first line, grab the second line, and then it says guess. So this says 10.89 months. So when x is 10.89 months later, right, we can figure out when this is. So this is going to be into the 11th month because she's paid halfway through the month. So we can see that we're already past the 15th because this is almost to the end of the month. So really, right, we want to look 11 months after she started. So if x equals 1 is June 15th, right, then we have July, August, September, October, November, December, January, February, March. We see that April of the following year is the 11th month. So in April of 2001, she'll have made $25,000. In January, her student loan payments begin. So she has a balance of $75,000 and her payments are $500 per month. Find a linear function for the balance on her loans. So we're going to assume Julie got an interest-free loan from a rich relative. So her loans aren't adding any interest. So she's just got to straight up pay the $75,000 for $500. So now the intercept of this line, right, is $75,000 because that's the balance that she had when we start. And now every month her slope is actually going to be negative $500 per month because the balance is going down. So her paycheck, she had a positive slope, right, 'cause she's making money. But here we're actually taking away from the balance when we make these payments. So we're going to call it 500. So we're going to write a function. F of x is going to be negative 500x plus 7,500. So the first month she'll knock $500 off, right? The second month she'll knock $1,000 off. So how long until Julie's balance falls below 50,000? So what we want to do here is we want to actually figure out, well, when does it equal 50,000? So let's go back to our calculator. And I'm going to go to my y equals and I'm going to clear out the first two equations. And now I'm going to put in my new equation, negative 500x plus 75,000. And then we're going to set this equal to 50,000. So paying $500 on $75,000 is probably going to take longer than earning $2,200, but let's just graph it to see what we get. And we see nothing at all. So the first thing we want to do is we want to try to zoom fit. So look what happens when I do that. So there's the balance falling. And there's the line. Look how far apart they are. They aren't going to intersect until way out here. So we need to adjust our X scale. So we only had about 18 months in here. So let's take this out to 60 months. That's 5 years. That's a car loan, right? Expensive car. So now let's try to graph it. And now we can see the intersection. So just to make this a little bit easier on us, I'm going to zoom fit one more time so it makes this a little easier to read. So now we can see the intersection nice and clean. So remember, you're going to have to play with the scales on these problems because you don't know the final answer. So sometimes you have to kind of do some guesstimates. So we're going to go to second calc. We're going to intersect. So grab the first line, grab the second line. It says guess, and it's exactly 50 months. So Julie's loan will take 50 months to hit a balance of 50,000. So we know anything beyond that, it will be below 50,000. However, we need to now express this in terms of time. So we're going to assume that her, we don't know exactly when she started paying off the loans. We don't know if it was the same week she got her paycheck, but we want to know how long. So 50 months, right? We know there are 12 months in a year. So 4 years would be 48 months. So this is approximately 4 years and 2 months. So typically on these problems, you're told specifically how to format your final answer, but a good rule of thumb when you're doing problems and you're solving for time, typically we keep converting time up to the next unit of time until the answer makes logical sense. So 50 months, that's sort of hard. You have to do some math in your head to figure out exactly how long that is. So once we get over a year, we usually go up a unit into years. And then if the years got really wild, crazy, out of control, we might go to like decades or centuries, right? Same thing if we got an answer that was 5,252 seconds, well, we might convert that to minutes or even hours until we started getting numbers that were reasonable and made sense.